Also, the previous, okay, I think it's turned on, so I will start today's class. So, what did we learn in the previous class? So we learned about the basic RISC-V instructions such as arithmetic instructions and memory instructions, right? Do you remember? So yeah. So as you can see, you can find the RISC-V instructions here. So I cannot use my pen and tablet here, unfortunately. So actually, we learned about this arithmetic instruction, and we did not learn about the shift instructions or logical instructions, but we learned about the arithmetic instructions, such as you can see, arithmetic instructions have add instructions. So we learn about the add. This is the different form, as you can see. And then, so we learned about the solve instruction here. So actually, this is the RISC-V integer instruction. So we do not have, and actually this type of instruction does not have multiply or divide instructions. So you can find the logical instructions here, and then also you can find the R format here. So I believe if you see these instructions, you can find some rules, like the format rules. So if you see the add instruction here, then you can find that this is the R type instruction. And then if you see the add is I is attached after the add instruction, then you can find that this is the I type instruction. So this is the different type of instruction. So you can find that many R type instructions here, like the XLL and then XIL. So you can find the I type instruction in the logical instructions like XOR, the exclusive or, and the AND instructions here. So actually, same type of instructions have the same format. Like if you see that this add instruction, you can find that the add RD, RS1, and RS2. So these operands of the add instruction represent RD means destination register, which means that the result of add instruction is stored to this destination register. So we also learned about the register in a processor, right? And then RS1, RS2 is two truth registers. So which means add instruction leave two operands data from register file, so which becomes RS1 and RS2, and then add performs this operation. So read data from register file indexed by RS1. This is the source register number 1, and then also the read data from register file indexed by RS2, the source register number 2, and then performs add operation. And then the result is stored to destination register. So R-type instructions have the same format or same rules. Which means, so if you see we did not learn about the exclusive OR, so but this is the logical instruction. So we don't know the meaning of the exclusive OR. So I believe some students already know about the meaning of exclusive OR. But if you see this exclusive OR instruction, you can find that this exclusive OR has the same R type, R format. So this means exclusive OR has also RD, RS1, RS2. So even though we don't know the meaning of the exclusive OR, but we already know that exclusive OR is the R type instruction. So which means exclusive OR read data from with two operands from register 5 indexed by RS1 and RS2 like here. It's the same format, right? But operation is different. Just operation is different. Exclusive OR perform, bitwise exclusive OR operation. Add instruction performs just add operation, right? It's very simple, right? So only this part is different here, and then the result of bitwise exclusive OR operation is stored to the destination register, right? And then we learned about the memory instruction. So in this keybook, load instruction and then store instructions are memory type instruction. Then what is load instruction? So we learned about the register 5. So I frequently use RF for the register 5. And then also we learned about the main memory. MM, so main memory. So what is the load instruction? The operation of load instruction, read data from main memory and then transfer the read data to register 5. So in order to store some data to the register 5, then we need to know RD. What is this? This is the destination register number, right? Also in order to access main memory, we require address, right? So in order to access data in the main memory, we need to access some space of the main memory with the address. So which means load instruction requires destination register number and address. Then how can load instruction calculate the target address? So actually load instruction calculate the target address as the offset and RS1. This is the source register number 1, and then this is the offset. So which means the load instruction reads case address, the data. So load instruction reads data from register 5, is indexed by RS1 and RS1, and then and offset. So offset is just the unsigned integer number. So which means actually unsigned integer number means that it includes the 0, so 0 plus natural number, right? So unsigned integer number. So sorry. It should be signed number. Okay, and we can also use the -2, something like that. So sorry about that. So we can use the signed number for the offset. So this is the signed number. So this operation is performed and then address is generated. So with this address, load instruction access the data in the main memory and then transfer data to the register file. Okay. So if you see the format of the load instruction, so you can find all this is the I format. Okay. So as you can see, this is I. So let's see the load word here. If you see the load word instruction, then you can find the load word as the RD, right? And then RS1 and immediate number. So immediate number means the offset. So I said that immediate offset is the signed number. So immediate number actually means the signed number. So what is the meaning of the load order? So this is M means the memory. And then, so as you can see, this is R means the register 5. So read data from register 5 indexed by RS1, and then this space address is added by immediate number, which means offset, and then hit this means this become address of load instruction, and then with this address, then access the memory, so main memory, and then store the read data to the destination register file. Okay. Then also there is a different instruction, different memory instruction. This is store instruction. Okay. So store. So in the previous class, I mentioned that the direction of the store instruction is opposite of load instruction. So what does that mean? So which means, so if we see the load instruction is data from main memory and then store the read data to the register file. Then opposite direction means store instruction read data from register file and store the read data to main memory. So it's the same. In order to access data from register file, we require register number, and then for the store instruction, this register number becomes the another source register, RS2, because, and then in order to access the main memory, store instruction also requires address, and then in order to calculate the address, the target address of store instruction, actually we use the same form, such as this one. So store instruction require two source registers, and then the second source register is used for the index of this register file. Okay. And then the first source register is used for calculating target address of store instruction. You understand? Okay. This is the store instruction. So actually there are two types of memory instruction, load and store. And then you need to remember the direction of the load instruction and store instruction. And then if you see it's a little bit small, I'm sorry about that. So if you see the store instruction, that if you see this store word, so you can find that store word has the RS1, RS2, and immediate RS. So which means, so as you can see, what is that? I think this should be RS2. So if you see that this meaning of the store word, then you can find that the RS1 store instruction generates the address of this target memory, the address of the target memory is the RS1 plus immediate. So this is the offset, and then so this is the target address in the main memory, and then with the data with the RS2. Okay, the source register number 2, and then the store instruction with data from the register file, and then the read data to store to the main memory. Okay.
Find the number.
Okay, so offset is the find number, which means that so this is the offset and then RS1. So this is the format of the address of store instruction and load instruction. So and then I explained that you can calculate the address of the store and load instruction like the RS1 and then plus offset. So let us assume that this value is stored in the register file. So let us assume this is the like the 1000. Okay, 1000 is stored in the register file, and then I said offset is the signed number. So this is the signed integer, which means 정수 in Korean. So offset means that, so if the offset is the +4, this is the positive number, positive integer. So if we use 4 as the offset here. And then this is just the immediate number. So we will learn about the immediate number actually in class, in this class. So if this number is 4, then we perform the, actually this instruction performs 1000 plus 4. So address becomes the 1004. But as I mentioned, we can use the negative integer like -4. So it's easy. So we can just use -4 as the offset of the this store or load instruction. And we can perform 1000 minus 4. This is the 996. Okay, you understand? So unsigned number means that we can use the unsigned integer as offset, and then we can just perform the add operation for calculating address of load instruction or store instructions. Okay. Okay. Okay, so yeah. So I briefly reviewed what we learned in the previous class. Okay. So we learned also about the register 5. We also learned about the memory instructions in register 5 ISA. Okay. Then let's compare the register and memory. So why do we use register 5? I already explained in the previous class. The size of register 5 is very, very small compared to the size of main memory. So as I mentioned, so actually even in our smartphone has 4 gigabytes or 8 gigabytes of main memory. So it's very large. So 8 gigabytes. So for example, 4 gigabytes. Okay, what is the size of a 4 gigabyte? So this is the byte. It's a 4 giga. Giga means 9, right? So it's the size for 9 bytes. Okay, the byte. But let's think about the register 5. So we learned about the register 5 also in the previous class. So I'll be 32. So 32-bit RISC-V integer ISA has the 32 general purpose register, and then the size of a single register is 32 bit. The 32 bit. So actually 32 bit is the 4 byte, right? Because 1 byte is 8 bit. So which means actually 128 byte, right? So let's compare the size of the main memory and then register 5. It's very, very small, and it's very, very large. Okay, but why do you need to use the register 5? If the memory size is very large, so which means that its memory is very, very slow. So which means that if the memory size is very small, then its memory is very fast. But as you can see in the RISC-V instruction table, you can find that many instructions access register 5, right? Only memory instructions access memory, load and store instructions. But for the arithmetic operation or some other logical operations or shift operation, these instructions access register 5. So which means, so if we see our program, so we can find that actually the small, if we just focus on the several lines of our code, This line is code just to access the several variables, right? So which means, and then as usually if we use some variable like ABCD, and then these ABCD are repeatedly used in our code. Okay, we just use the several number of variables in our code. So which means if this small number of data is stored in the register file, and then the data are repeatedly used by our RISC-V instruction, then we can execute these instructions very quickly. So in the chapter 1, we learned about the CPI. So this is very important for the performance of a computer system. So if instructions just access very large memory, the main memory, then CPI will be very large because the memory is very small, right? But if the instruction just gets at the register file, this is very small memory component, then instructions can access data in register file very fast, which means the CPI is small. If the CPI is small, then the performance will be high. Okay, so that's why we use the register file. But so actually, in the previous class, I mentioned that if we declare the variable like this, then I mentioned that, oh, this variable is stored in the main memory. Then how can we use register file? How can we? So actually we don't need to worry about the usage of register file. Then it's the task of compiler that you can see here. So compiler actually manages which registers will be used by your code. And so actually your code is translated in stuff by instructions by RISC-V compilers. And even though we use the variable like this one, then compiler just store this variable in the main memory. And if these variables are repeatedly used, then by using those instructions, this will actually every variable is stored in the main memory, and then these variables are transferred to the register file by load instruction, and then compiler manages which registers will be used by this data. Okay, so which means we don't need to worry about the register management. But if you are a compiler engineer, then you need to consider how to use register file efficiently. Okay, so this is called the register optimization. So this is the very important job of a compiler. And then let's learn about the immediate operands. Frequently erase my phone. So what is it? So actually you observe that immediate operands are used in the RISC-V instructions, right? Add I here, add I next. So if you see this RISC-V instruction, then you can find that this is the add I x22 and then x22 and 4. So this form of add I instruction is a little bit different from the add instruction we learn. Okay, so what is this operand? So the first operand means the destination register file. So we can find that 22 is the register number. The register number of the destination register. Also, this is the source register number x22. So it means that we can know that, oh, this add instruction with data from register number x22. And what does this mean? So you can find the constant number here. And then also this is instruction is the Fi. So which means this is the adding function that uses immediate number. So this small constant number included in the RISC-V instruction, any other instruction, is called the immediate number, immediate operands, what immediate number. So immediate number is the very small signed number, okay, signed integer actually. So what is the benefit of an immediate operand? So we learned that here, shift the a to 1, and then I equal I plus 1. So how can we compute this statement, with the RISC-V instruction? So if for this statement, so we can frequently observe statement like this, actually in a for loop. So I is here, and then we need to perform the plus 1. Actually, you can find this kind of statement very frequently. Okay. So now to compute this statement with the adding function, and so firstly, with the load instruction, we need transfer the I to the destination register of the load instruction, and then this is the 1. So which means actually if there is no immediate instruction, then we need to use another load instruction. Then with the another load instruction, then we need to store this operand 1 in the main memory, and then this data is transferred to the another destination register, and we need to perform this RS1, then this RS2, then RD. But as you can see, this is the very small constant number, and then we know that these small constant numbers are frequently used in our normal program code. And then after these small constant numbers are stored in the main memory, and then also the main memory space is wasted. But now to transfer data from main memory to the register file, we need to use the load instruction. Also, in order to store this small constant number, we need to place the entry of the register file. And then usually I said that this main memory is very slow. So which means the CPI of the load instruction can be very high. Okay, so that is it will degrade the performance of a control system, and then we don't want this situation. So instead of store this small number in the main memory, we can use the immediate instruction. So instead of using register from, then this small number can be stored in the instruction itself. So like that, we can just perform the RS1 plus 1 equal RD. Okay. So this is the immediate instruction, and then as I mentioned, we can use the small. So because its immediate operands are stored in the instruction. So we will also learn about the instruction format later. But instead of using the source register number 2, then the instruction has the small constant number, small signed number, okay? And then this number can be directly used as the operand of add operation. Okay, so this is the immediate operand. So as you can see in this table, so we can find the many immediate type instructions. So if you find this format I means the immediate instruction here. So load use the immediate instruction format. Also some other arithmetic or logical instructions here. So you can find that there are many immediate instructions at I here, and then exclusive or I. So this logical instruction has also immediate type instruction. So we cannot find sub I. Why? Why? We cannot find the sub I in the arithmetic instructions. Why? Because so as I mentioned, as I explained about the NI, so it's an ID, RS1, and the immediate. So this is the sign number. Okay, so I is just RS1 minus immediate. So instead of sub y, you can use the add I and then RS1 and then negative number for the immediate number, right? That's why we don't need sub I. Understand? Yeah. Okay, so we learned about the immediate number, and then I mentioned that immediate number is the signed number. So I briefly explain about the signed and unsigned numbers. So I believe you already know about the signed or unsigned number. Oh, so obviously computer system use the binary number. So which means that every digit of the binary number represents the power of 2. And it's the same to the decimal number. Every digit, like the one digit, if we see our decimal number system, like the 1, 2, 3, 4. So this digit means the 10, 0. Okay? And then this digit represents the 10, 1, and the 2, then 10, 3, right? And then it's the same to the binary number. Each digit represents the power of 2, and 2 to 0, 2 to 1, 2 to 2, 2 to 3. So like this. So it's obvious. So in the binary number system, each digit represents the power of 2, and then by multiplying the digit number with the power of 2, then we can calculate the magnitude of binary number. And then as you can see, this is the unsigned number, so which means that we cannot find any sign bit like the plus or minus. So actually, every digit represents the positive number. Okay, so which means so actually in the binary number, this digit is called the RISC-V. So RISC-V means this significant number, and then the first digit is called the MSB. It's called the most significant bit. Okay, so this is the RISC-V, and then this is the MSB. So actually, unsigned binary integer, MSB is the represent the positive value. Okay, so we can just calculate this MSB like this equation. If this has the n bit data, then the MSB equals this number multiplied by root n minus 1. So if we use the 32-bit unsigned data, and the range of the 32-bit unsigned integer is 0 is large number. And if you use the 64-bit, and then you can calculate the range of the 64-bit unsigned integers. the range is the 0 to n minus 1. N means the number of bits. So then, how can you represent the signed number? So in a computer system, we use two's complement signed number system. Two's complement means that only MSB is different. So MSB represents the signed bit of the two's complement signed integer. So if you see this equation, you can find that so this is the MSB. So you can minus sign is added in the MSB. Okay, which means the minus x. So this is 0 over 1, then multiplied by 2 and minus 1. Okay, so the range of this signed number is the minus 2 and minus 1, 2 and minus 1, minus 1. Okay, so what is different? So in the unsigned number, the range is the 0 to 2 and minus 1. Okay, but because in the signed number system, we use the two's complement number. So the MSB represents the minus and multiply with 2 and minus 1. So range becomes here. Okay, so this is the signed number. So actually, if we use the double word, so which means the 64-bit, then the MSB, the bit number 63 is the same bit. And then if we use the word data, which means word data has the 32 bits, so which means bit number 31 becomes MSB. So bit number, if we just see the MSB of the word data, it's the bit number 31, then we can find, oh, this is the positive number or this is the negative number. Okay. And then as you can see, the most negative number is the 10000. So this is because actually this number represents the minus 2 and minus 1, right? And then most positive is the 0, 1, 1, 1, 1. Okay, because this is the all positive numbers. And then how can we change the sign of the number? So we can use this equation. So this means the negation of each bit, the bit, each means the bitwise not. So actually we invert every bit of some number. And then if we just add 1 to the inverse bits, then we can change the sign of the binary number. So this is the two's complement system. So this is the example. So if you see that this example, 2 is the 0, 0, 0, 1, 0. So this is 2. And then if we just want to change the sign of this number, then we just inverse each bit. So you can find here, and then just add 1. So which becomes the 1, 1, 1, 1, 1, 0. So that is the sign negation. And then sign extension. Also, we need to also consider the extension of the sign bit. So for example, RISC-V instruction, load instructions has we have some different load instructions like LB and then LH and then LW. Okay, so the first L means the load. And then the second letter represents the B means the byte. H means the hash word. And then W means the word. So byte means just byte. It's the 1 byte. So which means the 8 bit. And then hash word is the 2 byte. And then word is the 4 byte. The hash word is because hash word because it's a half of word, the 4 byte. Then if we see the load instruction here, So what is the definition of load instruction? So load instruction is the main memory, and then load instruction read data from the main memory and then store the data to the register file. But then in this course, we are learning about the storage to bit register file integer item. So which means the size of a single register file is 32 bit, right? It's 4 bytes. So which means it's the word size. But let's think about the LB. So LB means that it's the load byte, so which it means read byte data from main memory and then store this data to the register file. Then what is the problem? The size is different. So this is the byte data. There is the 1 byte data. But when this byte data is stored in the register file, a single register file size is the 4 byte. And how can we deal? So actually, you can transfer 1 byte of data and then fill the some 1 byte with the that data. And how can you fill the remaining parts of the register file? It depends on the data type accessed by load instruction. Okay? So in order to fill the original space of the register file, then I said we need to consider the data type of the load instruction. So for example, if we just if the load instruction and we just handle the unsigned data, and then so this is the 32-bit register file, and then it just fill the first 1 byte with the read data from main memory. And how can you fill the remaining part? So this is this load instruction handles the unsigned data, and we just use the LB view. U means the unsigned sense, which means this is the MSB. MSB is the additive for the unsigned number. Then what should we do? The remaining part will be all zeros, right? Because when you learn about the unsigned number, then the magnitude of unsigned number is calculated like this. So if the MSB is 1, even though 1, then we cannot add any 1 to the remaining part of the register files because this is the unsigned number. But if the load instruction handles the signed number, so it's the normal case actually. So if we just use the normal LB instruction, then this is the signed number. How can we fill the remaining part of the register file? It depends on the sign of this data. Okay? So what does that mean? So if the MSB is 0, so which means it's the additive number, right? Then how can we fill the remaining parts? Because this is the positive number, so it's a 7 down to 0. So this MSB of this data is 0, which is actually minus 0 multiplied with 2 7. Okay. So 7. Oh, this is just 0, right? So we can fill the additional part of the register 5 with the 0. But if MSB is 1, if this means the negative, then how can we fill this part? If the photo byte data, so this is the prime number, and then it's MSB, the 7th bit, if bit number 7 is the 1, which means it's the -1 multiplied by 7, right? So actually, for this case, we need to fill the remaining part of the register 5 with the 1, right? Put it -1 multiplied by 2 to 7, and then if we just calculate this the magnitude of this part, then we can find that this is actually the same. Okay, so if this instruction handles the signed data, and then if we require to extend the bit resolution of our data, then we need to consider the MSB to expand the bit resolution of our data. So for example, if the MSB is 0, then if we just extend the bit resolution to from a byte to half byte to a byte to word, then we just fill the all zeros. But if the MSB is 1, and then if this is the signed data, then we need to fill the remaining part with the 1. Okay, and this is called the sign extension, binary data. Okay, so you just need to know that if we just handle the unsigned data, which is unsigned number, then for the extended extension, then we can just add zeros. But if we just perform the signed extension, then we need to consider the MSB bit. And by checking the MSB bit, then the remaining part is filled with the same data, actually same bit of the MSB here. So if the MSB is 0, then we just add all zeros. Then if the MSB is 1, then we just add all 1. Okay. So that's why this file supports the 2 different load instructions of the LB, the signed extended load byte, and then LBU is the so LBU just handles the unsigned data, so which means that it's a 0 extended load byte. Okay. So when we consider about the bit extension, then we need to consider some data type and then the signed bit of the signed data type. Okay, now let's see how the instructions are represented in a computer hardware. So why do we need to learn this representation? So actually, okay, now we learned about the assembly instruction of RISC-V. So which means that we just add learn like the add x1, x2, x3. So which means it's the add RD, RS1, RS2. But as you can see, this is the natural language, natural language word. So it's we can understand how this is the adding function. But actually in the chapter 1, we learned that in computer processor is the system. So which means computer processor can only understand binary number. Okay. So actually processor cannot understand this assembly instruction. So this assembly instruction needs to be represented using binary number system. Okay. And then so we will learn how to represent the instruction with the binary code. So as I mentioned, it's called the assembly instruction. And then if this assembly instruction is represented using the some binary code like 1111, 1111, and this data is called the machine code. Okay. Then computer hardware is it's just the hardware, which means that hardware has limited resources. So first, we need to set how many bits will be used for representing RISC-V instruction. So I said how many bits. How many bits will be used for representing machine code of RISC-V instruction? So actually, RISC-V is the RISC-V ISA. Then usually RISC-V ISA is the used fixed with instructions. So the fixed with, so which means in order to represent the one instruction, RISC-V use the fixed number of bits. So RISC-V use the 32 bits per instruction. Okay, the fixed bit. So it is 6 bits different, like the x86. The x86 instructions has a variable instruction length, but this is the RISC-V instruction, which one is instruction simpler. RISC-V instruction have fixed with instruction. Then RISC-V use 32 bits per instruction. Actually, it's the same to ARM ISA. ARM also use the 32 bits with for representing one instruction. Okay. So here is the it's a 32-bit instruction word. And then actually, so if we just use the 32-bit bit data like 0, 1, 1, 1, 1, then it's very long and we cannot easily recognize some position of bits with the binary number. So that's why we frequently use the hexadecimal number for representing instruction. Actually, so hexadecimal is the 16-bit base system. So 16 bits. So 16 base system. So actually 4 bits are represented using one hexadecimal number. Okay, 0 to n. So this hexadecimal number is CAA can be represented using binary number like this. Okay, but we can just decode the E is the 1110. So this first 4 bit is the first number of the hexadecimal number. First digit. Okay. Then let's see the format of the RISC-V instruction. I think I will choose a pen in this case. Okay, so if we see that this basic instruction format, we can find all this R-type instruction, I-type, S-type, and U-type. So actually use already so this R-type, I-type, S-type, U-type instruction is the RISC-V the instruction table, right? So we frequently find the this is the R-type instruction or it's the I-type instruction here. Then what does this mean? So if you see that this format figure, you can find this is the bit number 31. Okay, so bit number 31. This is the MSB of the instruction. And then we can find that this is the 0 bit. So it's a bit number 0. And then you can find several fields inside of this instruction word. So for example, if we see the R-type instruction here, so we can find this is the OP code field from 0 to 6 to 6 in number 6. And then this is the RD. So the RD represents the estimation register number, and then you can find the function 3. So it's a 3-bit field. Also, you can find the RS1 here, RS2 is here. We can find the function 7 is here. Then, what does that mean? So, we use the field to represent instruction. So, for example, this is the add instruction. So, RD, RS1, RS2. So we can find that if we see that this R-type instruction format, we can easily find that you can find ID here. ID is here, and then RS1 is here, or RS1 is here, RS2 is here, RS2 is here. And then, RISC-V has 32 general purpose register, 32. Then enough to represent 32. 32 means the 0 to 31. So enough to represent this number, we require 5 bits. Right. With the binary number from in order to represent the 0 to 31, we require 5 bits, right? So which means, in order to represent the RS2 number, so we require 5 bits, 5 bits, 5 bits. So if you see that this instruction format, you can find the ID and 5 bits of the instruction word. RS1 is here, RS2 is here. So with these 16 bits, we can represent the ID, RS1, and RS2. Then, which means with the remaining field, like OP code is here, in OP code, and then function 3, and then function 7, then we can represent the add. Okay? You understand? Then how about the I-type instruction? I-type, this is the immediate field, and then this is the Li. So if we see the Li instruction, or we can find the Li has the ID, RS1, then immediate number. And then this is the I-type instruction. So RD is here, RD is here, and then RS1 or RS1 is here. And then instead of RS2, then we can use the immediate number. But immediate number is the no signed number. So no signed constant number. Then how can we represent the immediate number? So if you see that this I-type field, you can find that we store immediate number in this field. Okay. So in the R2 instruction, this field is occupied by function 7 field and the RS2. For immediate type instruction does not require RS2 field. So actually, our I-type instruction occupies these parts of the instruction word to represent the 12-bit immediate number. It's a 12-bit. Okay. So because the immediate field is occupies the 12-bit, the range of immediate number is so this is the signed number, And then we can represent immediate number using 12 bits. Then what is the range of the immediate number? Minus 2 to 11 to 2 to 11 minus 1. Right? Right? Okay. Okay. So actually feature is that immediate number has just a range like the other binary number. So this is the hardware. So each type of each data type or each number type has some ranges. Okay. Limited ranges. So also, if we just change this ADI as the load instruction, like load work, LD, load word, then load word is also I-type instruction. So if you see the RISC-V instruction table, then you can find that load word is also I-type instruction. Then how can we assign this approach? So I is here, the RS1 is here, then immediate number is here. And then as type represents the actually store instruction. The store. So in order to represent the store instruction, so actually I need to check first. So if the store instruction has so I need to check the format of the store instruction. I will know in the next class. But if the store instruction has this format, then store instruction has actually two require two sort of registers like RS1 and RS2, and also store instruction requires the immediate number. But so in the R-type instruction, RD is here, and the RS1 is here, and the RS2 is here. And then actually the store instruction requires the two source registers. And the store instruction does not require only RD. So instead of RD, this RD is occupied by the lower part of the immediate number. And then also the upper part of the immediate number occupies the function set field of the R-type instruction. And then RS1 and RS2 is located here. So if you see the RISC-V instruction format, then you can find that opcode is always here, the lower part of the instruction word. And then usually RD extension register number is here. And then RS1 is here, and RS2 is here, usually not always. So it means actually the RISC-V instruction needs to maintain the regularity of instruction format. So it means that opcode is always the lower part of the instruction word, ID is here, and so on here. And then some instruction have the variant formats like I-type or U-type instruction. The immediate number can be assigned to the unnecessary part of the instruction here. Okay. So this is the R-type instruction. So okay, I will show you here. I will show you this one. Let's focus on the add instruction. So this is so if you see the add instruction here, so you can find the add instruction is the R-type instruction. And then we already learned that RD, RS1, RS2 can assign to some field of the instruction word. Then I explained that in order to represent the add instruction, we need to use opcode field and the function 3 field and the function 7 field, right? You can find the here. This is the opcode field and then function 3 field and then function 7 field. So if you see the add instruction here, the OP code is the 0, 1, 1, 0, 0, 1, 1. And then in order to represent the add, we use the function 3, like 0, 0, 0. And then function 7 field is the 0, 0, 0, 0, all zeros. Okay. So which means if we just assign this OP code and then function 3 as the all zeros and then function 7 as the all zeros, and which represent add instruction. Understand? Then what's the sub instruction? Sub instruction is also put alpha instruction. So ID RS1, RS2 has the same format. So which means that these ID RS1 and RS2 are assigned to the same location of the instruction word. And what is the difference? We need to use the OP code function 7 and function 3 and the function 7 fields to represent the sub instruction. So if we use the sub instruction, so actually OP code is the same, right? Same to the add instruction, which one here's the same color here. Even the function 3 is the same. And then function 7 is default. Okay. So like this, we can translate the assembly instruction to the machine instructions. Okay, based on these instruction format rule. But if you see the these RISC-V instruction table, then you can find that there are some rules, right? So by the color of this instruction format and the code. So if you see some if this is the alpha instruction, so you can find that. So I format instruction of the shift instruction, arithmetic and logical instruction, and then some compare instruction, the OR, we can find the same color here, has the same OP code here, right? And then if the immediate instructions are used, OP codes are different. Okay. So if you see the add and add I, we can find that OP codes are different. Okay. Also, if you see the load instruction here, the load instruction is some different category. So you can find that even though the I format is the same, the load instruction is the I format instruction, but OP codes are different. Okay. So there are some rules the I's are designed. So actually the first rule is the regularity. So actually it is 5 for use the same location for RS1, RS2, and RV, which is the number. And then OP code is used for classifying different category of instructions. So we use this OP code for the load instruction. We use this OP code for the store instruction, and we use this OP code for some R-type instructions. These instructions are called the R-type instructions. This is the arithmetic, logical, shift and compare instructions of the R-format instruction. So for this type of instruction, we use 5 use this OP code. And then for the immediate instruction, this 5 is this OP code. Okay, and then you will learn about this control instruction. Control instruction can also be from OP code. Okay, so usually OP code of this 5 items represent the category of some instruction, a class of instruction. And then in the same class of instruction, with this 5 distinguish the different instructions in the function 3 or function 7. Okay. Some encoding rule of the specified instruction. Okay. So I will stop here and do it for some not broken. I think I don't know why, but my pen didn't work. I'm sorry about that. Then do you have any questions? Okay, thank you for your attention and see you in the next class.